So what we are looking at is a volume question from the BGCSE 2002 paper 3, and it reads, the diagram shows a beaker which consists of a cylindrical container with a hemispherical end of radius r, and the capacity of the beaker is 300 centimeter cubed. When the beaker is filled with 240 centimeter cubed of water, the level of the water is 2 centimeters lower than the brim as shown. And then we have the diagram of the whole situation there. And on my right here, I have the surface area and volume of solids formulae. They come from the mathematical formula for paper 3. And so what I've basically done, I've written down the information we've been given, the capacity, the volume, and the height of the empty cylinder. So part A of the question says that what volume of water do we need to fill the beaker completely to capacity? Well, that's basically the capacity of the beaker, which is 300 minus the volume of the water. That's already there. So to answer part A, we just subtract 300 centimeter cubed with 240 centimeter cubed, and that is 60 centimeter cubed. And then part B, show that the radius r is equal to 3.1 centimeters, correct to two significant figures. For this one, what we can do, well, we know that the volume of a cylinder, although not, I don't think it's given here. No, it's not given here. So the volume of a cylinder is given by pi r squared h. So we can use this part, we can use the empty cylinder, this one, to calculate the radius using this formula. We know that the capacity is 300 centimeter cubed, and having taken the volume of the water that's already there, we know that the volume of the empty cylinder is 60 centimeter cubed. So from that we can, and knowing that the height of this empty cylinder is 2 centimeters, we can calculate the radius r. So the volume is 60, and then that is equals to pi times r squared times the height, which is 2, and then dividing both sides by 2 pi, basically making r squared the subject. We have r squared being equal to 60 over 2 times pi. Then we take the square root both sides, we can find r. And if I punch that on my calculator, the square root of 60 divided by 2 pi, I get 3.0901. So 3.090193616, and approximating that to two significant figures gives me, this is in centimeters, gives me 3.1 centimeters, which is beautiful because this is what the question asked me to find. So I write 3.1 centimeters as required, hence shown. And then for part C of the question, well, it's always a good practice to write down the whole digits on the calculator. In my case, I'm using a sharp calculator, so it displays 10 digits for the sake of accuracy. So throughout the question, I'll be using those long digits and then approximating at the end. And then for part C of the question, calculate the volume of the water that can be held in the hemispherical part of the beaker. Okay, interesting. So we already know the radius. It's approximately 3.1 centimeters. So to find the volume that can be held by the hemispherical part of the beaker, we must remember that a hemisphere is just half of a sphere, and knowing the volume of a sphere, we can derive the volume of a hemisphere. So the volume of a sphere, as you can see, the volume of a sphere is given by 4 over 3 pi r cubed. If we divide that by 2, we get, you divide by 2 here, you get 2 over 3 pi r cubed. So this becomes the volume of the hemisphere. So knowing that the volume of the hemisphere is 2/3 of pi r cubed, we can say, well, we know that r is 3.1, so we can just cube that. So 2 over 3 times pi times 3.1 cubed. When computing this, I'm not going to use 3.1. I'm going to use that long answer. So I've just saved it in my calculator. I've just stored it, and I'm just going to retrieve it and use it to compute. But to avoid wasting time, I'm just going to write the shorter version when displaying my calculation. And then I work that out. I have 2 over 3 times pi times 3.1 cubed. That gives me 61.80387.232, which is approximately, to 3 significant figures, is 61.8. Well, the units are centimeter cubed, so that is my answer. And then quickly moving on to part D of the question. Show that the height of the cylinder is 7.9 centimeters, correct to 2 significant figures. To do that, let's see. So the height of the cylinder, we are looking for the height of the cylinder. This is the height of the cylinder, right? So they're saying we must show that it's 7.9 centimeters. To do that, the route that I'm going to take is to say, well, I know that the capacity of this beaker is 300 centimeter cubed. So if I subtract the volume of the hemisphere, which we have just calculated and said it's 61.8, part C of the question was asking us to calculate the volume of the water held by the hemispherical part. So if then I subtract from if I subtract the volume of this part, the hemispherical area, from this capacity, I get the volume of the cylinder, the capacity of the cylinder. So to do that, I say, well, I know that the beaker can hold 300 centimeter cubed of water. Subtracting the volume of the hemisphere, I get 238.1961277 centimeter cubed. Remember, I'm using the longer version, this part. I'm using this part to compute. So I get this, and then, well, now that I got it, I can just round it off. So rounding it off, I have 238 centimeter cubed. Oh no, show that the height of the cylinder is 7.9. No, I don't need to round that off. My bad. I don't need to round that off. I'm looking for the height of the cylinder. So this is the capacity of the cylindrical part, right? And I know that the volume of a cylinder is given by pi r squared h, right? So knowing the volume and knowing the radius, I can easily find h. So I just make h the subject of the formula. So h is just the volume of the cylinder divided by pi r squared, and the volume of the cylinder is 238.1961277 over pi times the radius is 3.1. So squaring that, I'm going to get I'm going to get 7.93987093, and then I approximate this, I get 7.9 centimeters. So the units here are centimeters. And what did the question ask me? To show that the height of the cylinder is 7.9 centimeters to two significant figures. This is what I've just shown. So as required, or you can just write shown, right? Okay, so let's be quick. Part E of the question asks us to calculate the outside curved surface area of the first of the cylindrical part of the beaker. So part E of the question. So we want to find the curved surface area of the cylindrical part of the question. So the curved surface area of the cylindrical part is basically a rectangle. Like if you take this cylindrical part and then you split it up vertically and open it up, you're going to have a rectangle. And then this part here will be this part. Let me change the color. That part will be this part here. So it will be the circumference. And we know that the circumference is 2 pi r. And then this part here will be the height. So this is the height. And to calculate the curved surface area, we just calculate the area of that rectangle, which is 2 pi r times h. That is 2 pi r h. And we know all those values from the previous questions. So all we do is just substitute 2 pi times the radius is 3.1, and then the height we calculated to be 7.9. But I'm going to use the longer versions. So I'm going to say 2 pi times 7.93 and the other digits times 3.09 and so forth. And then I'm going to get 154.1625913. The units are squared. and then I simplify that, I get 154 centimeters squared. I'm simplifying that to 3 significant figures, right? So we have done just this. Okay, we have done this part, this part, this part, this part, this part. Now part 2 of E says we must find the outside capped surface area of the hemispherical part of the beaker. Now the key to this question is also realizing that a hemisphere is just half of a sphere, and knowing that the total surface area, as we are given here, the total surface area of a sphere is 4 pi r squared, we can just divide that by 2 to get the total surface area of the total capped surface area of a hemisphere, right? So that is the capped surface area of a hemisphere is 4 pi r squared over 2, which is 2 pi r squared, and then substituting that's 2 pi times 3.1 squared, and then punching that onto the calculator, we have 60 on the spot. So we have 60 centimeters squared, because this is area. And then we are done with this part of the question. Now the last part F says that the total outside capped surface area is to be coated with a layer of silver at the cost of 45 thebe per square centimeter. So calculate the cost of the silver coating to the nearest thebe. Okay, so we have done the part of calculating the outside capped surface area of both the cylinder and the hemisphere. So if we add that and then multiply by 45 thebe, then we are done. We have basically calculated the cost of silver coating the outside capped surface area. So part F, we just add so let me just label this capped surface area 1, and then this one is the capped surface area 2, right? So for the cylinder, capped surface area 1, capped surface area 2. So for F, we just need to add capped surface area 1 with capped surface area 2, and then multiply that by 45 thebe. So that is 154.16259113 plus 60 times 45 thebe. Then I compute that, I get 96 spooler. So this is 96 spooler and some other numbers. Because this is money, I rounded off to 2 decimal places. So that is 96 spooler 37 thebe. And that's about it. We have solved the whole question, and we should be guaranteed with the whole marks. Until we meet again next time, God love and stay winning.